Hi, thanks to the organizers for this opportunity. I see that several of the talks in this session are on time-dependent density functional theory, which is a topic that is close to my heart. But actually today I'm going to tell you about some of our other work, which is also in dynamics, but it's on the exact factorization approach. So the problem in my mind is quite general. We're interested in we want to solve for the time evolution of a system of a coupled quantum subsystems. And these could be, for example, different kinds of particles like electrons, nuclei, and photon, with little q being the coordinates of all the electrons, big Q being the coordinates of all the nuclei, etc. Or we could just have perhaps one type of particle, for example, all electrons, where little q could represent occupation numbers in a subset of the orbitals, for example, weakly correlated ones, and big Q could represent the occupation numbers in, for example, this other orbitals, the strongly correlated orbitals. Now, if we were to try to solve this, it's not only too computationally expensive, but also we would sort of have way too much information than we might possibly want. We might be interested in just one part of the system. For example, if our system of electrons and nuclei, our molecule is subject to a laser field or subject to a photoabsorption, we might be primarily interested in what the nuclei do. So clearly it's very influenced by the electronic motion after the electron is photoexcited, but we might not want to care too much about the details of the electronic motion, but we want to know what happens to the chemical reaction to the nuclei, and therefore the influence of the electrons on the nuclear motion. Or if we just, going back to the situation where we just have electrons, we might want to treat, for example, part of the system, like the strongly correlated orbital occupations, as at a higher level of accuracy than the weakly correlated ones, like in the spirit of embedding methods. And so a useful framework for this is the exact factorization approach, where we factorize the wave function as a single product, where we put the variables that we're interested in the marginal factor and the rest in the conditional factor. And I'll tell you more in detail about this factorization shortly, but just to point out that when we do this, we find that there's a Schrödinger-like equation for this marginal factor alone. And therefore, so in other words, for the one subsystem that we have a particular interest in, and the potentials that are appearing in that Schrödinger equation exactly incorporate the couplings from all the other subsystems. So this can lead to a lot of insight into how correlated motion affects dynamics of different subsystems. But a more practical goal is to then start to approximate these potentials and the coupling terms in the equations to lead to practical dynamic schemes, such as mixed quantum classical schemes. So that's kind of exact factorization conceptually. And I'm going to now come to the outline. I'm going to tell you a bit more detail about how it works for the standard problem of just electrons and nuclei, then extend it to photons to look at cavity QED problems, finding the time-dependent potential driving nuclei, and the time-dependent potential also driving photons in this case, and I'll motivate these studies as we go along. So again, considering the original problem, actually, when we deriving the exact factorization, was that of a molecule or a solid where you have electrons and nuclei, and our Hamiltonian contains or consists of kinetic energy of the electrons, the nuclei, and all the Coulomb couplings between the constituents, between all the charges, and possibly laser fields being applied to the system. So there's an explicit time dependence also in the Hamiltonian, possibly. And the point is that the solution of this very many-body wave function can be uniquely written as a single correlated product of a marginal factor of the big R coordinates, the nuclear coordinates, and a conditional factor in the Hilbert space of the electronic coordinates, little r, but parametrized by the nuclear coordinates, or conditionally dependent on the nuclear coordinates. And in fact, this conditional factor then for this product to be unique and meaningful, as we'll get to in a second, the conditional factor satisfies what we call a partial normalization condition. You integrate it over all electronic coordinates for a fixed nuclear configuration. For every fixed nuclear configuration in time, you get a 1. And so this makes it unique up to a phase transformation, which depends on the nuclear coordinates in time, that you can put in one factor and take it out of the other. Okay, so the point is that when we do this factorization, one can show that the nuclear factor can be interpreted as a nuclear wave function, meaning that its modulus squared gives you the correct many-body nuclear density, and its phase gives you the many-body nuclear current density. And the nice thing about the equation that arises, the exact equation for the marginal, is that it solves a time-dependent Schrödinger equation. So with potentials which are modified from Born-Oppenheimer or other approximate methods, but these potentials depend on phi. So actually, this factorization to a single product might be reminiscent of the Born-Oppenheimer approximation, but this is definitely not a Born-Oppenheimer approximation in any sense. Just definitely isn't one, because for one thing it's time dependent, another thing is it's actually exact representation, and we're going to see in the equations that you can see that the terms in the equations go way beyond Born-Oppenheimer. Okay, so I'll come back to these potentials in a second. The electronic wave function, however, satisfies a more complicated equation. In both the equations, the coupling terms depend on the other wave function, so they have to be solved self-consistently, if you like, or they have this self-consistency in their form. So the equations look like this, right? As we said, if we look at the second equation first, it's got a Schrödinger-like form with a scalar potential epsilon, which we call the exact time-dependent potential energy surface, with a analogy, if you like, to the static Born-Oppenheimer potential energy surfaces. This is again very different, because the exact surface here it involves the full time-dependent conditional electronic wave function, not Born-Oppenheimer wave functions, and it involves the electronic Hamiltonian, which is not just Born-Oppenheimer. In some sense, you can think of the zeroth order term as Born-Oppenheimer, but there'll be corrections coming from these funny coupling terms, which depend on the parametric dependence on the conditional wave function. I'll come back to this in a second. Actually, let me just highlight here the terms which represent the couplings between the system. So you can see that the electronic wave function, conditional wave function, appears in the nuclear equation, and the equation driving the electronic motion involves this nuclear quantum momentum effectively from the nuclear system. So there's really intimate coupling between the two systems, right? And so also in the nuclear equation, we have a vector potential, which can be interpreted as an exact time-dependent Berry connection. But in the equations are also form invariant under gauge-like transformations. So for example, you can, as we mentioned, you can multiply the phi and the chi by a R and T dependent phase here, and the opposite one for chi, and the vector potential and time-dependent potential energy surfaces transform in this way. And so sometimes, in fact, in the examples I'm going to show you, I can always gauge away my vector potential and then just study the exact time-dependent potential energy surface as a indication of this electronuclear coupling. So I'll come to that in a second. So this approach, these equations, what they mean for coupled dynamics has been studied in all sorts of different directions, actually. So one question is, the vector potential, when can we gauge it away? How does it compare to the adiabatic Born-Oppenheimer geometric phase effects that occur? And there's been several works on that. There's been work done on looking at mathematical stability of the two equations as you propagate side by side. Unfortunately, they're not very stable, and meaning that this doesn't represent a practical reformulation of the exact problem. Rather, that it's again to give insight if we can somehow extract these coupling potentials, but also to be a starting point for approximations. One can also switch the roles of the electronic and nuclear coordinates using the electronic coordinates as a marginal factor, and this is particularly important if, for example, we're interested in ionization processes, where we want to focus in on what are the electrons doing influenced by the nuclei, then we get potentials that drive the electrons. You can also, as we mentioned before, just take one type of particle, just the electrons, factorize amongst themselves, and this electron-electron factorization has been useful to provide an alternate picture, for example, to the single active electron for strong field physics. Okay, I mentioned also electronic embedding. Lionel Lacombe has done a factorization in Fock space to set up a method to deal with strongly correlated systems, coupled to weakly correlated, to deal with strong correlation. The system of equations has been densely functionalized, and what I'm going to tell you today is extensions to include photons as well in sort of this burgeoning field of molecular polaritonics, which I'll get to shortly. As I mentioned, in all these different approaches, you gain some insight through these potentials into correlations of motions and when you have coupled quantum subsystems. But a more practical impact is that they provide approximation. They provide the starting point to make approximations. So actually, because this has perhaps the most practical impact, I just want to flash up one result or one example of this. There's been a surface hopping method based on the exact factorization, where you take a mixed quantum classical, you take a classical limit of the nuclei of the exact factorization equations, and do some and consistently treat the electronic equation. Then you find a modified electronic equation and also a modified nuclear equation. If you replace the nuclear equation with the surface hopping scheme, and we find a method called SHXF, derived by Sing-Kyu Min in South Korea, and we have recently applied this actually to dynamics through a three-state intersection in the uracil cation, and we start in the D2 state after ionization and photoexcitation, and you find that the populations transfer through a three-state conical intersection. You can see that D0 and D1, the exact reference here is in solid MCTDH, grow sort of simultaneously near this intersection. And if you track which of these surface hopping methods is capturing this dynamics, well, you see it's the one with a triangle, which is this SHXF, while the other methods, which are either just plain surface hopping or decoherence correction surface hoppings, these corrections tend to be rather ad hoc, that completely do not get the dynamics well at all. So we see this sort of profound influence of the exact factorization term in determining the populations here. And I think later in the session, Shane Parker will tell us more about surface hopping, the algorithm itself, and how to get some improved hopping probabilities. And here we just simply used the traditional surface hopping probability, but coupled to the exact factorization electronic equation. Okay, so back to the main part, I would like to tell you now about how to extend, or what extensions of this approach to look at photons. And so here, we're now going to motivate this by saying, well, why do we really care? Well, there's this sort of in the past decade or so, maybe a little longer, there's sort of been a rekindling of interest in cavity QED problems. You know, it's been known for really the early days of quantum mechanics that Purcell realized that if you confine a resonator to an optical cavity, you can drastically enhance spontaneous emission rates, right? So this strong light-matter coupling achieved through confinement in the past decade or so has been exploited to sort of change light matter or manipulate matter properties using vacuum fluctuations of the radiation field, giving the possibility of sort of a cleaner control at sort of no input power than with laser fields. And as a sort of an example to make this a bit concrete, here's one of the early papers. And in fact, earlier in the session, also Davis Weluka gave a really nice talk on this, on the cavity QED and the change in lifetimes of resonances, line shapes of resonances due to strong coupling. But in this work here, they looked at this ring opening process of spiroperan and tamarocyanine, and it turns out that if you have a sample of these outside the cavity, or spiroporene outside the cavity, and you apply some UV, the molecule opens up into this myrcene form here. The absorption spectra, this is the absorption spectra of spiroporene, and this is of myrcene. And so you get this, if you have a mixture of these, and you get both of these formed because, in a mixture where you're supplying some UV photons. And the point is that if we then put the system in a cavity at a resonant frequency corresponding around this region here, we see that the absorption spectra changes in this region. This resonance, or this absorption peak, splits into two. And moreover, what we find is that the photoisomerization rate of the process drastically slows down in the resonant cavity. If you put it in, if you change the width of the cavity, it's no longer resonance, you no longer get this effect, but you get this real suppression of this chemical reaction, essentially by the confinement. And this is just one example of many new phenomena. Listed some of them here: enhanced conductivity, enhancement of ferromagnetism, for example, in different scenarios where people have confined their system in an optical cavity or in a nanoplasmonic system to make use of this strong light matter coupling. And sort of a key concept is having resonantly coupled quantum subsystems. So you have a molecular transition with a certain frequency, and just like and you have a cavity resonance at that same frequency. And so just like when you bring two hydrogen atoms together and you to form the molecule, you get these split symmetric, anti-symmetric states. In here we're bringing again, it's a resonant effect of a molecule this time, and a photon mode. We get split hybrid states called polaritons. These have mixed mixed light matter character. But of course, the molecule for a given cavity is only resonant at some nuclear configurations, and this is what leads to the distortion of the potential energy landscape, and which ends up changing the chemical reaction. So the simplest Hamiltonian for systems of this type, of correlated nuclei, electrons, and photons, is non-relativistic. We neglect spin coupling, we neglect any cavity losses, make the dipole approximation the length gauge, and you pop out with this Hamiltonian here, which has the usual matter part, then the photon part, which we can write as a series of harmonic oscillators using the displacement field coordinate, where A and A dagger here, and raising and lowering operations for a photon mode. Q is this combination here, and P is the conjugate variable. This is related to the displacement field. This is related to the magnetic field. The coupling between the matter and the photon has a bilinear form under these approximations, where you have its dipole coupling coupled to this electric field or displacement field type coordinate with a coupling strength that scales as 1 over the square root of the volume, getting larger as the confinement gets smaller. There's also this very interesting term, the self-polarization term, which is very important, and it can be very important and interesting in the sense that it involves only the matter coordinates. However, it depends on the coupling strength. So it's sort of a photon-mediated self-polarization of the cavity of the matter. Okay, so to include photons, we then turn to our factorization, and we have now a third degree of freedom. So we have sort of different options of how to factorize. And these aren't the only ones, because we could further nest the factorization. But for example, we could factor out and take the marginal to be the photonic system. And in that case, we would get a Schrödinger equation for the photons. And this would give us then an exact potential, which drives the photonic motion. And in fact, we've looked at this recently and shown that it can explain errors in when people use this Hamiltonian and simulate problems using classical treatment of the photons. So I'm hoping to get to that. Then we could also factor out the nuclear degree of freedom and get the Schrödinger equation for the nuclear system. This gives you an exact potential that drives the nuclei when coupled to electrons and photons, and you could also, of course, get the electron factorizer, couple out the electronic system. You get the idea. So I'm going to focus first on the exact potential driving the nuclei when coupled to electron and photons. And so perhaps the first thing that we might like to ask ourselves as well, first, what is the analog of the Born-Oppenheimer approximation here? now we have photons, so what would we do here? So just like in the Born-Oppenheimer approximation, where we take the full Hamiltonian, subtract out the kinetic energy of the nuclei and diagonalize that to get our Born-Oppenheimer states and surfaces, we do the same thing here, but now our Hamiltonian includes the polaritonic harmonic oscillator and the couplings, right? So, but anyway, the point is the photons are treated then quantum mechanically on the same footing as the electrons to get these polaritonic surfaces. So I'll show you what these look like for a very simple model, but first the model without any cavity. What is this model? It's the 1D Shin-Metyu, one electronic coordinate, one nuclear coordinate in between fixed ions, but it's not so important what the model is, more perhaps what the Born-Oppenheimer surfaces look like. They look like this, so that, for example, if we start off with a nuclear wave packet photoexcited, with an electronic excited state, we see that it'll slide down the surface, meet this region of non-adiabatic coupling, and some of the population, electronic population, will transfer to the lower state. Some will stay on the upper state, depending on how fast it's moving. And one can see then in the insets here that I've pictured the Born-Oppenheimer states for these different surfaces. And over here, we see that the electronic state is more or less localized on the left, whereas if it makes the transfer, the electronic surface is localized more on the right of the electronic subspace. So this would be a proton-coupled electron transfer if we get this population transfer. If it stays in the upper surface, it still is localized on the left. So there's no, it wouldn't be an electron transfer. And so if we look first at the black surface here, which is hiding behind the orange, I'll tell you about that in a minute, we see this coupled transfer, the change in the dipole moment to the electrons as well as the nuclei. Now, if we put the system in a cavity, which is resonant with this frequency here, we find a suppression of this proton-coupled electron transfer at this cavity, at this coupling strength. At the weaker coupling strength, however, we see that very little difference. And so this then makes us see, well, what do the polaritonic surfaces look like? Are they very different in these two coupling surfaces? Here are the polaritonic surfaces, which are defined just before, and you see that they're not, to the eye, they're essentially the same. Of course, the character, as we move along these surfaces, is quite different. It depends on where we are and which surface, but they have a sort of a mixed photon matter coupling character. But you can see that they really have they really look very similar, for these two different coupling strengths, and it's difficult to see that they would lead to such different dynamics here. However, if we now turn to the exact surface, the time-dependent potential energy surface that's driving the system here, we see that these surfaces actually do make the exact time-dependent potential energy surface does distinguish these two cases. So here I'm going to show you a plot with the polaritonic surface in the background, and then over up here we'll have the exact time-dependent potential energy surface. Let's see. Here we start. In the red is the case of inside the cavity, in the black is cavity-free, and the nuclear densities are shown here. So this is the initial time. They're basically on top. The initial state is the same. And we see that after very short times, this exact surface, and this is for the stronger coupling strength. The weaker coupling strength is, in fact, if I did the same plot, it's basically on top of the cavity-free case. But you can see that already the curvature is changing here, making the left part of the wave packet move slower than the right, develops further this very distinct kink structure where the different slopes means that the left part of the wave packet essentially is trapped on the left while the right part keeps going, kind of like the cavity-free case. So, so you get this transfer. You get this suppression, this bifurcation of the nuclear wave packet in the cavity-free case that doesn't occur in the full cavity case. Okay. So in fact, if you want to read more details of how that works, and as we mentioned, the exact surface can be decomposed into these different parts. We can look at, you can look at the paper where we show these different features of we analyze exactly the surface in terms of like the weighted Born-Oppenheimer term, or weighted, in this case, weighted polaritonic, and then these other terms that are inherently including the electron-nuclear coupling. But I want to actually show you now something, the same problem, but now if we instead look at the surface, the potential that's driving the photons. And for motivation for this, then had noted that the photonic parts of the Hamiltonian are harmonic with bilinear coupling. In other words, it's completely quadratic. And we know that an older result from Rick Heller back in the 70s showed that for for problems where we have a harmonic quadratic at most Hamiltonian, and you sample the Wigner distribution and run classical trajectories from that, this is what multi-trajectory Ehrenfest does, you can get the exact dynamics. And however, so then the question is, if we do this for our problem, do we get the exact dynamics, the exact photon number? And in fact, we don't. The black, if we want, the black here is the exact, and the pink is the cavity-free, and the dark blue gives this method where we're treating the photons with Ehrenfest dynamics, with Wigner sampled classical trajectories, while the light blue is treating both that and the photon nuclei, but we don't need to worry about that for now. But notice that the photon number is greatly underestimated when we treat it via Ehrenfest. So this suggests then that the exact potential that drives the photons is not harmonic. And so the question is then, what is it? So here is again our factorization, and we want to focus on the photonic system. So we choose this as our decomposition, and we're going to look at the Schrödinger equation and the potentials for chi of q, the displacement field density, the photonic density. And we might first, before I show you this in a simple model system, we might say, well, do we really care? And in fact, we do, because especially when we do have, in typical cavities, we have really an infinite number of modes, right? And we have to figure out, the influence of many modes on the dynamics. So how do we account for these? We can't really treat them all quantum mechanically, and something that's been explored recently is treating them exactly in this Ehrenfest way. And it was noticed, in fact, in this work here, that in doing this for 400 modes and 2-level systems, 3-level system for your matter system, you find it a similar underestimation, about 2/3 in photon number. And also recent analysis of vibrational strong coupling in real systems actually use classical trajectories on the Born-Oppenheimer surface, and these are really nice calculations of Subotnick group, for example, and others. But we want to get a sense of the size of the error in these calculations. In fact, I won't talk about this much at all, but if you do have many modes, the self-polarization term becomes very important. And so we'd like to understand that better, what you can get dramatic changes, and how does this influence the dynamics, right? So I'm going to pick an even simpler system to look at here, which is a 2-level system coupled to a single resonant cavity mode. And we start with the 2-level system excited and no photons in the cavity, right? So here's our Hamiltonian, bilinear coupling, photons, electronic system. And what we expect to see is that there's a spontaneous emission, and there's basically Rabi cycling, then a reabsorption of this photon. And so what we're going to do is find the exact QTDPES, meaning that TDPES that's driving the photonic system from the exact factorization. We're going to classically evolve photons on this and compare with MTE. So if you are, I think I'm going to run short of time, but here are the sort of equations, if you like. And if we want to note that we could sort of decompose and compare, and in this work we did this, compared the structure of the equations to sort of interpret the results a bit better. And for example, we can take our conditional electronic wave function and sort of expand it in these QBO states, if you like, with Q-dependent coefficients. And in the MTE, you don't do this. You take a trajectory for each photon, if you like, and expand that. And this gives sort of very big differences in the potentials that are sort of underlying the dynamics. So the results look like this. Here's our this is we're moving to a half cycle. So the photonic density here in black, the exact quantum density, it is a ground state of the harmonic oscillator. As one photon is excited, you get to as the photon is emitted, you get to the first excited state, like this over here. And you can see that in the top figure, we've plotted the MTE trajectories, and it completely misses the structure of the photon excited state. if you then look at the middle panel here, this shows the quasi-classical trajectories as evolved on the exact time-dependent potential energy surface. And here we see that we do kind of get a structure, and sort of not quite exact it's classical motion that doesn't get, for example, the region and sort of middle part well, because essentially what's happening is actually we can understand what's happening by looking at the QTTPS. A barrier grows in the middle, which gets quite large, and essentially what happens is that it shuns the photonic density away from the middle region. And in the classical case, for classical trajectories, they can't live in this forbidden region, and so you sort of get this exaggerated structure, whereas the quantum dynamics has some tunneling, and you get a higher probability in the middle. So this is leading to the difference. But again, the main point is that the exact surface driving the dynamics is really far from harmonic. MTE cannot generate the barrier it essentially sees, and again, in here there's more detail, harmonic potential that just kind of spreads out a wee bit, and so therefore you get a smaller photon number. If you like, we can have a look at the movie, but I think we've more or less covered that in the figures, and then there's a movie for the photonic density in the MTE, which simply just spreads, and so this gives us incorrect or underestimations of the photon number. Okay, so here's a summary, but I'm out of time, so I'll just flash it up here, and then just maybe give my thanks to the organizers for this nice session. This is the group at Rutgers from this spring, and we're also working on TD-DFT. Davud had a talk in the DFT sessions about this, as well as exact factorization in different flavors. But the work I presented here was done by Lionel Lacombe, who is a postdoc recently, but now as a Marie Curie Fellow at École Polytechnique. Nora Hoffman, who is a joint PhD student with Angel Rubio, now a postdoc at Columbia, and Bart Rosenzweig, who is actually an undergraduate student at Hunter College and now a math PhD student at Ohio State. Thanks. I'd like to thank my funding and you all for listening. Thanks.